Hello everyone. Today we present the glass bulb system. The fundamental mechanism is thermal radiation or incandescent well electrical resistance with a conductive wire generate heat and visible light. Historically, Thomas Edison integrated a durable filament with a controlled vacuum to delay material degradation. Today, it holds a modern niche role in specialized applications like incubator and industrial oven where thermal byproduct is the primary asset. Moving to the product overview, this interdependent mechanical system operated as a highly integrated assembly rather than a standalone wire. It faces an extreme thermal environment requiring the tungsten filament to exceed 2500 degrees Celsius. This creates an oxidation challenge as atmospheric oxygen as this extreme indicates immediate rapid oxidation. Thus, this glass envelope acts as a critical isolation barrier, retaining the protective atmosphere and excluding reactive external gas. Regarding material, this glass envelope uses standard soda-lime glass, perfectly balancing optimal transparency, cost-effectiveness, and formability. The core channel constitute our silica sand establish the foundational structure network soda as a fluxing agent to effectively lower the melting threshold and limestone to improve chemical durability and stability. Other key elements include the tungsten filament, copper or aluminum base, and an argon-nitrogen gas environment. Glass production begins the blending in continuous operation, where automated facility yields thousands of units per minute. Step 1 is raw material preparation. Bulk quantity are weighed using automatic local cell and rigorous precision to prevent dimensional optical defect. Step 2 is mixing and coolant integration, homogenizing the batch with a specific ratio of recovered broken glass. This offers a great economy benefit as cold requires significantly lower energy input to melt, enhancing plant sustainability. Melting. In the melting phase, the homogeneous batch is continuously fed into a large-scale furnace. For thermal regulation, natural gas burners maintain internal temperature approximating 1500 degrees Celsius to live key solid particulate. During the refining phase, trapped volatile components and microscopic gases including migrate to the surface and dissipate. This avoids a major quality risk, as reacting gases include mechanical weak point and severely distort optical quality. During forming molten glass is extruded into a continuous high-velocity ribbon. The ribbon meshing process synchronizes the scanning blow heat and scanning precision mode. A precisely timed pneumatic injection of compressed air and force the malleable glass to form to the interior mold cavity. The strict requirement here is flawless mechanical synchronization, which is mandatory to guarantee completely uniform wall thickness. Next is annealing, which addresses the stress problem caused by rapid, uniquely thermal contribution between the exterior surface and interior matrix. The risk is that unrated bulb exhibit extreme brightness and spottiness fracturing. The solution is the annealing layer, a controlled thermal grading tunnel that gently reheats and slowly cools the envelope. Following a strict thermal profile, bulbs are cooled uniformly from the 550 degrees Celsius down to 25 degrees and completely relieve resistant stress. Finally, for quality assurance, automatic inspection system utilizes advanced optical sensor and laser profiling. Defect scanning actively monitor for dimension irregularity, gaseous inclusion, and microfractures. Through closed-loop recycling, non-complicant units are immediately cooled, pulverized back into coolant, and redirected to primary furnace. This recycling mechanism provides excellent resource optimization by effectively negating all raw material waste.
In this section, I will explain the production of the tungsten filament, which is the component responsible for generating light inside an incandescent bulb. Tungsten is selected because of its excellent physical properties, especially its extremely high melting point of approximately 3422 degrees Celsius. This allows the filament to operate at very high temperatures without melting. The process begins with tungsten ore processing. Raw ores such as wolframite and scheelite are crushed into fine particles and then separated through several concentration processes. The concentrated material is then converted into pure tungsten powder through chemical and reduction processes. This powder becomes the raw material used for filament manufacturing. The next stage is powder pressing and sintering. First, fine tungsten powder is compressed inside steel dies using hydraulic presses under extremely high pressure. This creates a compact shape known as a billet. At this stage, the billet is still very fragile. To increase strength, the billets undergo a process called sintering. During sintering, the material is heated to temperatures just below tungsten melting point of 3422 degrees Celsius. The extreme heat causes atomic diffusion between particles, creating strong bonds and eliminating internal air pockets. As a result, the material becomes much denser and stronger, making it suitable for further mechanical processing. After sintering, the tungsten enters the wire drawing stage. During wire drawing, the tungsten rod is pulled through a series of progressively smaller dies. Each die reduces the diameter of the material until an extremely thin wire is produced. Because tungsten becomes brittle at room temperature, heating systems are used throughout the process to maintain sufficient plasticity and prevent cracking. The final wire often reaches diameters smaller than 0.05 millimeters. Once the required diameter is achieved, the wire proceeds to the cooling stage. Automated winding machines wrap the wire into a precise spring-like structure. In modern incandescent bulbs, a coiled coil configuration is commonly used. A primary coil is wound again into a secondary coil. This design reduces heat loss, improves efficiency, and allows a longer filament to fit inside a small bulb. Finally, the filament undergoes quality control procedures, including checks for diameter uniformity, coil geometry, and electrical resistance. The final component in this section is the support wire system. Support wires hold the filament in position, reduce mechanical vibrations, and absorb thermal stresses generated during operation. These wires are commonly manufactured from nickel-coated steel or molybdenum alloys because these materials maintain their strength even under extreme temperatures. Despite their small size, support wires are essential for maintaining filament stability and durability.
In this part of the project, I will talk about the manufacturing of the electrical connection system of an incandescent light bulb. My section has three main parts: base manufacturing, lead wire manufacturing, and soldering operations. First, I will start with the base, also called the socket. The base is metal part at the bottom of the light bulb. Its job is connect the bulb to the lamp holder and carry electricity for the filament. Most incandescent bulbs use screw-type base made from the aluminum, brass, thin steel sheets. These materials are chosen because they conduct electricity well, resist rust, and are not very expensive. The manufacturing process starts with raw material preparation. Aluminum or steel sheets with the correct thickness are selected and prepared for production. Choosing the right material is important because it affects the quality and strength of the final product. The second step is stamping. In this process, metal sheets are placed into stamping machines and round metal pieces are cut from the sheet. Stamping makes production fast and accurate. After stamping, the metal pieces go through deep drawing process. During this step, the flat metal piece is shaped into a cylinder. This creates the main body of the socket. Deep drawing is one of the most important manufacturing processes because it gives the socket its final shape. The next step is thread forming. Screw threads are made on the outside surface of the socket. These threads allow the bulb to be easily installed and removed from a lamp holder. Finally, the socket goes through surface finishing and inspection. Sharp edges are removed, the surface is cleaned, and protective coatings may be added to prevent rust. The finished parts are then checked to make sure they meet quality standards. The second topic is lead wire manufacturing. Lead wires are small copper wires inside the bulb. They connect the filament to the base and allow electricity to go through the bulb. Copper is used because it's a very good conductor of electricity. The process begins with copper preparation and refining. High quality needed to good electrical performance. The copper is then made into rods which are used for wire production. Next, comb wire driving. In this process, copper and rods pull through the series of dies to make them thinner. As the rods becomes thinner, flexible copper wires are produced. During production, the size and quality of the wires are checked regularly. After the wire drawing, the wires are cut into the required lengths for the bulb design. The final topic is soldering operation. Soldering is used to connect the lead wires, the filament system, and the base. This process is very important because it completes the electrical circuit inside the bulb. The first step is positioning. All components are carefully placed into correct positions before soldering starts. Correct positions is important for reliable electrical connections. The next step is solder application. Solder material is added to the connection points and heat is used to melt it. This creates a strong connection between the components. After soldering, the joints are allowed to cool down and become solid. This creates a stable connection that can work safely during operations. The final step is inspection. The soldering joints are checked visually, electrically, and any problems are found are fixed before the bulb moves to the next stage of production. To summarize, the main manufacturing process in my section are stamping, deep drawing, thread forming, surface finishing, wire drawing, cutting, soldering, and inspection. Together, these processes create an electrical connection system of the incandescent bulb and make sure that electricity can safely reach the filament. Thank you for listening my part.
All right, moving on the next step, which is gas filling process. To protect the filament and make sure it doesn't burn out right away, we first need to remove all the oxygen and moisture from the bulb. We do this by using special vacuum pumps. Once the inside is completely clear, we fill the bulb with a mix of inert gases, mainly argon and nitrogen. This step is very important to protect the filament and improve insulation. Finally, we apply heat to compress the glass stem and create a completely airtight seal. Now let's look at the final assembly stage. As you can see in the diagram, this is where all the parts came together. First, we mount the filament onto the support wires so that it stays stable. After that, we apply adhesive to attach the glass bulb to the metal base. We then use a heat treatment process to dry the glue and create a permanent bond between the parts. To finish the assembly, we connect the wires to complete the electrical circuit. Of course, quality control is a huge part of the manufacturing line. As shown in the picture, we use industrial cameras for the automated optical check. This helps us quickly find any small cracks or mistakes on the bulbs. Next, we test the electrical parts to make sure that power levels are correct and any bad units are automatically rejected from the line. Finally, we take random samples from the batches and test them continuously to see how long they last. To wrap everything up, this project shows how we manage the whole production line from start to finish. It is a great example of different areas of engineering work together in harmony. Even though these traditional bulbs are being replaced by LEDs today, the automation and quality systems we studied here are still the foundation of modern manufacturing worldwide. On our last slide, you can see the academic references from our project. Thank you so much for listening, and please let us know if you have any questions.